I'm recording it now. Between two parallel plates. Okay, and I got to draw the springs. And there's the ball. Oh, no, 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 no. Don't want that. A different color. Everything's got to be colorful. Okay, so that's the spring constant for each. They're identical springs. The details are found in the diagram. Okay, 10 to the negative 3. The details are found in the diagram. The electric field is turned on with a corresponding voltage. So there's a voltage difference across here. That's 450 volts. They're not fooling around. Okay, and we also know that this is 0.1 meters across. That's very important. All right. And we know that this side is positive and this side is negative. I hope you can see that in the diagram. And when we turn on the electric field, okay, when we turn on the electric field, the ball moves to the right. Okay, so the ball moves to the right. So I'm going to draw the and then it stops. Okay, and then it stops. So that's very important. And the other thing I'm going to remind you kids, because some of you lost some marks on your assignment last time, is I've got it on the assignment in yellow. Show all your work, show all your steps, no shortcuts. Okay? So, 1A, it says calculate the electric field. Right? That's our required. Calculate the electric field. Okay? Well, the first thing you got to remember is if you take a look at this plate, you got the right-hand side's got the positive and the left-hand side's got the negative. By definition, now let's see who's been really following along here. By definition, the electric field, okay, has to go in what direction? Yeah, because it's all based on a positive test charge. Whoever said that, you're brilliant. Okay? It always is based on. So you have to ask yourself, if I put a positive test charge, in what direction will the force be? Well, it'll be to the left. So that means literally in here, the electric field is to the left. So what I'm going to do just to establish is I'm going to call this direction right here positive x hat. So positive x hat to the right. The electric field is to the left. Okay. Then it says calculate the electric field. So we already got the direction part, right? Because look, I'm asking for the electric field. It doesn't say give me the magnitude of the electric field. It says give me the electric field. So it's got a vector direction. It's a vector. It's got a direction. So I got that covered. We just did that. Okay. Then, and I don't want to give this away, but I will tell you this much. If you know the voltage, and we do, and you know the plate separation, right? What's the distance plate to plate? And we do. You can calculate the electric field because you got to remember when you look at electric field units, okay? Does anyone know what the typical standard unit for an electric field is? Just speak up. Yes, buddy. Newtons per coulomb, right? So it's telling you how much force is applied to an object for every 1 unit of Coulomb that is upon it, which is not really mysterious to your kids, to you kids. Look, G. Think about the unit for G. The unit for G was Newton per. Hello? Yeah. Because it's telling you how many newtons of force are applied on an object for every 1 kilogram it has. So look, electric fields or gravitational fields are all about how much force do you get per unit of the quantity that is causing the force, right? Electric forces are caused by charge measured in coulombs. Gravitational forces are caused by mass measured in kilograms. So there's a definite similarity here, right? Definite similarity that has to exist. And I hope you've seen that similarity in general when you compare F big G to FE. I hope you've seen the similarity there. I know we're going a little sidetracked, but anyway, it's good for you. So the reason I bring this up is, oops, someone just came into class. The reason I bring this up is this is the standard unit for electric field, but electric field can be expressed as another equivalent unit. Does anyone know what that is? Terrific, brilliant. So there's your hint for A. Okay, now B. Calculate the electric force on the ball. Okay, well, kids, this is not moving, it's stationary, right? That means its acceleration is equal to 0. And I'm only going to be worried about x acceleration. We're not worried about y in this one, okay? There's no y motion here, okay? We can get into that later, okay? So, acceleration is 0. And this is basically a one-dimensional question. So, you have to draw a free body diagram, right? You have to draw a free body diagram. So let's think about force from the spring that's on the left side and force from the spring that's on the right side. So the force of the spring on the right side, since you're compressing this spring, right? You're compressing this spring. The spring is going to push against it. And on the left-hand side, you're stretching the spring, so the spring is going to want to pull it back. Force left. Okay? And remember, it's moved by, what was it? 1 centimeter, right? So it's moved. As soon as you turn on the electric field, it moves by 1 centimeter. Right, so that's 0.01 meters. It's moved by that, okay? So that means this spring that's causing the force right, okay, it's going to have a compression of 0.01 meters. The left-hand spring, it's going to have a stretch of 0.01 meters. So that means you got to find out what each of these forces are. And that, of course, leads us to our friend, Hooke. Do you remember Hooke, kids? Hello? Hello? You guys remember Hooke? I hope so. All right? Okay. So, and this is not moving. So that means, you know, the electric force pulled on this, the electric force pulled on this until it got to a point where it was balanced out by the other two forces, and both of those forces came from the springs. So at this point right here, we no longer have any motion. Acceleration is 0. It stopped right there. Okay? So now, kids, listen. Let's see if you've been listening to me for 2 years. I've drawn a free body diagram. I say acceleration is 0. What do we use next? F net equals ma. F net, and this is all in the x direction. I'm not going to write it, but it's all x, is equal to the sum of all forces, right? You've seen this before in math class, have you not? Have you seen this in math class? It's for what we call a series. Do you know this? Sequences in series, do you know? I need feedback. No? You haven't seen that? Okay. Right? Do you know? Okay, this is the, what course do we do this in? Data. So Aiden, have you taken data yet? Okay. You're gonna give me a stroke. Anyway, this is the Greek letter sigma, the capital letter sigma, right? Okay. All right. So kids, I'm telling you, you should be able to find force electric, right? Now, Sonny, you asked for this question, right? Is this helping you so far? Okay. And then look, now I'm kind of leading you down the garden path here, right? I'm trying, like, here comes Peter Cottontail, hopping down the bunny tail. Hippity hoppity, the physics solution is on its way. I'm kind of leading you through. You need A, then from A, you you'll probably need that in the future. Okay, now you're going to calculate something in B, you'll need that in the future. So look, in A, we got this. In B, we got this. Well, that's kind of a hint that you're going to need these two to solve C. That's all I'm going to tell you on that one. Okay, I'm going to stop my recording. I'll post it later.